This question is titled, How do I use pipelines to pass data and coordinate processes? It turns out that one of the biggest things that we use shell for, and our mindset behind why we choose to use shell in the first place, is about formulating control flow and data flow pipelines so that we have one process that controls another process, or we have one process that passes data to another process. And there is a core concept of the shell that is unnecessarily controversial. People complain all the time that the shell is untyped and unbuffered. And they say, why can't the Unix, Linux shell be like PowerShell and pass rich objects around? And there is a very good reason for this. And if you try to fight this, you'll end up having a worse time than if you just learn to live with it. And you learn why it is that it is the way it is. Fundamentally, when you have two processes and you've connected them via a pipeline that is not text data that they are passing between them, it is a raw, untyped binary data. There are no types there. It might be human readable or decodable as human readable data, but fundamentally it's just arbitrary bytes that are being passed back and forth. And people get frustrated because they have to use all these contortions, awk and sed and cut and JQ and all these mechanics. And they say, well, why couldn't I just pass rich data between these two shells? Why couldn't I pass JSON? But if you really think about why this is, the shell and this approach of passing raw byte data from one process to another has withstood the test of time. How old is JSON really? How old is a shell script? How old is shell scripting? JSON is not 40 years old. A shell script from 30 years ago might still run today. You don't even have code that uses JSON from 10 or 15 years ago. And what does shell scripting look like in 15, 20 years? Maybe a slightly refined version of what it looks like today, but the code that you wrote 10 or 15 years ago will still run. Is JSON still going to be around in 10 or 15 years? Who knows? One of the fundamental reasons why the shell is unbuffered and untyped in terms of the data that it passes around is if you were to type this, if you were to pass rich objects around, which type system do you use? Whose objects do you use? When you think about PowerShell, PowerShell makes sense as patching rich objects around because it's all built on a common language runtime. So the kinds of types you can create in VBScript are understandable from C#, are understandable from PowerShell, and there is a common baseline. But the Linux Unix shell is in fact intended to allow you to stitch together software that is decades apart than when it was first written, that is wildly different in the programming languages that are used, that are wildly different in the type systems. And so if you were to trivially say, oh no, JSON's good enough, remember, JSON can't even represent dates. So how do you pass dates in your JSON data? Well, you have to assume, okay, we'll ISO format them. JSON can't represent even close to the fidelity of what Python can in its data. You can't represent sets in JSON. You have to represent them as lists. You can't even have mappings in JSON that aren't mappings of strings to numbers. So very simple things that we just take for granted in Python are non-representable in JSON. And you can see the moment you decide I'm going to use one type system and pass typed data around, you're making compromises. Because if not JSON, if it's the next level, well, what is it missing that one of the two programs can represent nicely that they want to preserve? And so what the shell did is said, I'm going to find the lowest common denominator. And the lowest common denominator is passing bytes around. And I'm going to create as a burden on both sides their ability to interpret this. You can think that this is actually kind of interesting. You see this at the hardware level as well. You often see that very successful hardware standards are ones where the cable is dumb and the controller is smart. And there are much more sophisticated standards where the cable has to be smart, but the controller is dumb. And what you can think is the shell is an approach where the controllers have to be smart. The controllers have to be a little bit expensive. They have to have the knowledge of what the data is that's being passed, but the cables are any old cable. And you've lived in the world where the cables have to be smart, and you've lived in the world where you're like, oh, this might be a USB whatever cable, but it doesn't actually work with my Nintendo Switch. Oh, it doesn't actually work here. Oh, it's Gen 3.2. What does that even mean? The smartness of the cable adds enormous complexity. The shell is a simple cable with smart controllers, and the controllers on either side are generally only as smart as they need to be to get their narrow form of work done. And they can be arbitrarily smart because the moment you create a brand new programming language with a brand new type system, well, you just take in the bytes and you lift those bytes up into something typed, and then you emit bytes again. So it creates this very primitive common denominator, but a universal one that has stood the test of time. And this is, I think, probably one of the core ideas behind shell. And this is why, for example, if you want to trigger commands from Python to execute something, well, you see, when you run a command, you get a byte string back because that's what the shell operates on. But let's shift our attention to this topic of how do I trigger things from the shell? How do I run things from the shell? Because it turns out if you had a Python script, there's 3 ways to do this. You can use subprocess.run. You can see when you do subprocess.run, it just emits the output, and it gives you a result with the return code. You could use subprocess.checkOutput that gives you the output, and here you can see the byte string. Or you could use subprocess.checkCall, which emits the same output and gives you as a result the return code. And shell's a little bit different than some of the other tools. 0 means successfully run, 1 means unsuccessfully run, or any non-zero value means unsuccessfully run. But you can see we can trigger things from the command line, from Python, but we're still responsible for interpreting those results, for parsing them. And yes, that can be a headache, but it leads us into a view of how do we actually trigger these by itself? Because we'll talk about what we need to know in order to use the shell effectively, and one big portion of that is to figure out how to create smart interpreters on either level or ad hoc parsing on either level. But narrowly focusing on just running these, I want to show you something that you can do from Python that is just very complex to do anything more than the most trivial example. Here is a Python script that runs 3 commands, and it runs 3 commands within other Python processes that it runs. Here, I'm going to go through these 3 commands, 1 + 1, 2 × 2, and 3 cubed. I'm going to open a Python executable, and I'm going to communicate with it. So this Python executable is going to be running in parallel with my existing Python executable. I'm going to pass data to this thing and then pull the data back out. And I could do this with multiprocessing, but here you can see, multiprocessing assumes that everything's Python. Well, this happens to be Python, but this could be, this could be just as easily a, Z shell process, as long as I make what I pass to this thing valid Z shell. So do something like this. And here that should work just as well. And you can see with this popen.communicate, you can communicate back and forth. But what's kind of tricky is to communicate simultaneously with the long running process. .communicate waits for the process to end. And what if it is that you want to feed a little bit of data to this running thing and then wait a little bit and do something else and come back and feed a little bit of data? And that starts to get very clumsy with popen. One thing that happens to be very clumsy from the shell is what happens if you need to connect the processes in a very complex fashion. Like you want the data from this to go to here and also to here, and the data from this to go to here and also to here, and the data from this to go to here and there. And that can be a little bit problematic to do. It can be a little bit tricky for you to do. And this is one case where the execution, the running of things, may actually end up being a little bit easier in pure Python. Let me show you an example. I find that popen is just far too sophisticated for my small brain to wrap itself around. It's just too much going on. And part of this is because it's cross-platform, so it works effectively as well on Windows and Mac and on Linux. But largely for my use cases, I don't really have execution environments on Windows. I don't really have execution environments on Mac. I'm more than happy to just limit myself to my Linux dev server. In that case, I often find that I drop down to the base level fork exec pattern. Here you can see a Python script, and it forks. It starts a child process. And if we're in that child process, it replaces itself using this exec call with another process, namely a Python script running a sleep command. And here you can see I forked and I created another sleep command. And this is kind of like what I did before when I do like a sleep 5, sleep 5. Well, it's a lot easier to do this at the shell, as long as I don't need to pass complex data between these, or at least I don't have to pass these in complex ways. Because you can see here, when I run this and I look at my PS tree, you can see both of those 2 Python processes are running at the same time. It's a lot of verbiage, a lot of noise for something I could do really simply at the shell. But what I could do if I wanted to connect these in a non-linear, non-standard pipeline is I could start two different processes, seq to generate the numbers from 1 to 10, and sed to take something that's passed in and to just annotate it with something at the beginning of each line. I could create pipes, unnamed pipes. I could create operating system connections between these processes with a read end and a write end. And this is the read and the write end to go from process 1 to process 2. These pipes are unidirectional in that there's one read end and one write end. You can only read from the read end, you can only write to the right end. And so you write to the right end and you read from this. And so this doesn't allow bidirectional communication. This is really a pipeline where something writes over here and then keeps going. But if you wanted to, you could enable bidirectional communication. It's just a little bit tricky to do. Here, I have a pipeline that's going to go from process 2 back to the parent. And I can set these as inheritable, and I can start each one of my processes and have it write out to the standard out of something else. Here, this is just starting the parent process and one of the processes. You can see it connected the output of one of these to the parent process's standard in, and I can read from the standard in. Generally, the mindset with the shell should be thought of in terms of how do I be just a little helper, a little unit in a complex pipeline, reading from my standard in to generate to somebody else's standard out. And then where you're adding additional functionality is the launching of these processes and the connection of these into a pipeline. And so we see when we see things like our command helper pattern, the command helper pattern is really just, generate one step of this that emits something, which you then pipe to something else. This is the proper shell mindset, accepting that it is an untyped, unbuffered pipeline and writing your tools as just little steps in that pipeline. And so it is the case where I'm always a little bit skeptical if somebody has a shell script that doesn't write anything interesting to the standard out or doesn't write anything interesting to the standard error. That probably means that it has an executor in there. And if it's both setting up what it's doing and executing it, there's got to be a good reason why it needs to do both of those steps. Because that makes it very difficult for you to intermediate between the two and say, set up the task, but execute it differently. Only execute these portions of the task. Well, where Python might still appear here is if I want to set up a more complex pipeline that I can express easily with the shell. Because I can say A goes to B, goes to C, goes to D in a very simple linear pipeline. But if I wanted to say A goes to B, which then branches off to D and E, which then branches out again, I'd have to use something like T, which can be a little bit clumsy. And if I wanted to make this a cyclical graph, which is possible to do, you can have cyclical pipelines, it's almost impossible to express this in shell easily. Whereas in Python, it's very easy to do. You just set up some pipes and just connect them as you go. And you could even use network-x to do this automatically. You can even have network-x build the graph and then for each one of the nodes in the graph, create the process, launch the process as using fork exec and then connect the pipelines. But that's a little bit too noisy for us to show you in a simple example. Here is our continuation of the simple example, and I'll show you taking this process, connecting it to this process, taking this process, connecting it to the parent process, and you can see 1 to 10, annotated by my second process, passed to my Python process. This ends up being something which is not too hard to do with the fork exec pattern, but is one of the reasons why you might drop into a proper scripting language like Python rather than shell scripting, because these kind of connections, beyond the simplistic, become really tricky to do. You can only have one co-process in a bash or Z shell script, whereas here, you can think of this as having multiple co-processes that might be arranged in different ways. I could, if I wanted to, take that write end and have multiple process ones write into the same write end. That's fine. So here I could have, sequence 1 to 10 and 10 to 20. And setting that up with a shell would probably require like a subshell with their own parent, with their own child processes, and it gets very finicky to control. Whereas in Python, it's nearly trivial for me to express that idea. And so when we think of the shell, what we're thinking of is fitting ourselves into this human augmented automation, where we're largely working within the constraints of this untyped, unbuffered pipeline, and we're usually either adding a little notch into that to process something along the ways. It has to be a smart controller because the underlying cable connecting the two units is just raw byte-level data, and where if we don't need to do the execution, then maybe we just emit some commands which are then later executed. But if we need to control the execution and we need to control how the data and control flow is set up, we might actually want to go a little bit beyond shell scripts, still use the individual computational units of shell scripts, but have some controller that's written in a proper programming language like Python.